Hi Andy. In the last class we discussed some concepts from NMR spectroscopy. Okay, nuclear spin is the basis for NMR spectroscopy. Okay, nucleus possesses spin angular momentum and magnetic momentum. So the ratio of those two is said to be gyromagnetic ratio. Okay. Next, we discussed quantum approach and classical approach. According to quantum approach, if you take a nucleus with spin quantum number I, it's split into 2i plus 1 levels in the presence of magnetic field. After that, if you apply radio frequency radiation, spin inversion takes place. So whenever resonance condition occurs, whenever radio frequency radiation matches with energy gap, okay, then spin inversion takes place, or say then radio frequency is absorbed. Next, how to get a spin quantum number if both the protons, number of protons and number of neutrons are even, I value is 0, that is NMR active or magnetically active. If you take odd, number of protons are, number of neutrons are odd, integral spin, number of neutrons even, odd or odd even, in such case spin quantum number is half integer. Okay. Classical approach. According to classical approach, if Larmor pressional frequency is equal to the the frequency of radio frequency radiation, then signal is observed. Okay. Next, to chemical shift. We are not giving absolute pressional frequencies, but we are giving frequencies, pressional frequencies with respect to a reference compound. So the difference between pressional frequencies of sample protons and reference protons, that is called chemical shift. Chemical shift in Hedges is equal to new sample minus new reference. But the drawback is chemical shift, if you express in Hedges, that it depends on field and frequency. So to overcome that, we expressed chemical shift in ppm scale, parts per million, that is new sample minus new reference by new instrument in megahertz. Okay, then we will get in ppm, and this is also in hertz, or chemical shift in hertz by instrument frequency in megahertz in ppm, and but if you substitute instrument frequency also in hertz, then we have to multiply with 10 power 6. Okay, tau means what? 10 minus delta. Tau scale means simply 10 minus delta, that is called tau scale. On 100 megahertz instruments, 1 ppm is equal to 100. On 60 megahertz instruments, 1 ppm is equal to 60. On 150 megahertz instruments, 1 ppm is equal to what? 150. 2 ppm is equal to 300, like that. And okay, right. Okay, so next one is what is the generally used reference component? What is the generally used reference compound? So after this class, I will give some practice questions also based on all spectras. Okay, reference compound. Generally used reference compound is tetramethylsilane. Generally used reference compound in NMR spectra is tetramethylsilane. So this is the generally used reference compound. What are the advantages we have with the tetramethylsilane? Why we are specially using tetramethylsilane as a reference compound? If you see, some advantages are it is highly inert compound. It is inert compound, so it may not react with the sample molecules, and it may not react with sample molecules. It is inert compound. That is the first advantage we have. The second advantage is its boiling point is low, around 27 degrees centigrade only. So it is easy to remove tetramethylsilane after recording spectrum from sample, and easy to remove after recording spectrum from sample since its boiling point is low. The next one, important one, is it possesses How many protons? And 12 protons. All these 12 protons bonding connectivity is same or not? Yes, all these 12 protons bonding connectivity is same. So we have 12 equivalent protons. We have 12 equivalent protons, okay, in tetramethylsilane. So that means, what about the intensity of this signal? And intensity of this signal is high. Why intensity of the signal is high? Since that signal is corresponds to 12 protons. That signal is due to 12 protons. All the protons resonate at same frequency. All these 12 protons resonate at same frequency. So intensity is very high. So it is easy to identify the signal corresponds to reference protons from sample proton signals. We can easily identify reference proton signal compared to sample protons signal. And okay, that is another advantage we have. Next one, all these 12 protons are highly shielded. And highly shielded. If electron cloud is high around the nucleus, then such protons are what? Highly shielded. Then generally we will get in upfield or downfield. And upfield, their expressional frequency values are low, their chemical shift values are low. That's why they get in upfield or high field. Okay, here CH3 and CH3 is what? Electron donating group. CH3 is what? Electron donating group. So therefore, what about these 12 protons are highly shielded. So therefore, we will get in the high field. And high field, and its intensity is low. Okay, so easy to identify the signal corresponding to tetramethylsilane. And sample protons are generally observed in low field or down field with respect to reference signal. And generally sample proton signals are observed in down field or low field compared to a reference proton signal. And another advantage is its solubility. And okay, most of the organic compounds are soluble. It is soluble in almost all organic solvents. And okay, that is another advantage we have, right? These are some advantages we have, that is soluble in organic solvents. But if you go to aqueous solvent, water for example, okay, if you are recording spectra in aqueous solvent, and if sample we are taking in aqueous solvent, in such case this is not suitable. And if okay, it is almost soluble in all organic solvents. So if you record NMR spectra by taking organic solvent, generally we follow tetramethylsilane. If you take aqueous solvent, in such case we follow DSS, and that is 2,2-dimethyl 2,2-dimethyl 2-silapentane 5-sulfonic acid, sodium salt of 2,2-dimethyl 2-silapentane 5-sulfonic acid, that we follow in aqueous medium. And okay, 2,2-dimethyl 2,2-dimethyl 2-silapentane 1, 2, 3, 4, 5 sulfonic acid. So 2,2-dimethyl, okay, next to 2-silapentane 1, 2, 3, 4, 5 2-silapentane 5-sulfonic acid, sodium salt of 2,2-dimethyl 2-silapentane 5-sulfonic acid. This we use in the case of aqueous solvent. So this is about a reference compound. Generally used reference compound is tetramethylsilane. These are some advantages we have with the tetramethylsilane. Its solubility, it is soluble almost in all organic solvents. Next, it possesses 12 equivalent protons. So the intensity of signal corresponds to reference proton is high. Easy to identify the signal corresponding to TMS. Next, all the 12 protons are highly shielded. So generally we will get reference proton signal at upfield, sample proton signals downfield or low field compared to tetramethylsilane. Generally tetramethylsilane frequency is fixed at what? Instrument frequency 0 ppm. Okay. Next one, factors affecting chemical shift and factors affecting chemical shift, factors affecting chemical shift. In that first one, electronegativity. Already we discussed yesterday electronegativity. Factors affecting chemical shift, electronegativity. If proton is attached to electronegative atom, okay, if proton is attached to electronegative atom or electron withdrawing group, then what happens to electron cloud around the nucleus? And electron cloud around the nucleus decreases. Whenever electron cloud around the nucleus decreases, effective magnetic field felt by the nucleus increases, so precessional frequencies increases, so chemical shift values increases. And so whenever proton attached to electronegative atom, then what happens to chemical shift values? Increases. And for example, we have like this, and CH3F, fluorine, chlorine, bromine. If you take, what about electronegativity of fluorine is more compared to chlorine compared to bromine. So therefore chemical shift values for these protons, okay, in this order. As electronegativity of atom increases, chemical shift value also increases. And for example, proton is attached to oxygen and at nitrogen, and where chemical shift is high, oxygen is more electronegative compared to nitrogen. So if proton attached to oxygen, okay, its chemical shift value is more. Okay. Next, as the distance okay, if you are taking like this, and CH3 CH2F, as the distance between proton and electronegative group increases, then its effect decreases, and its effect decreases. So here we have two types of protons, A and B type of protons. Okay, the bonding connectivity is different for these two sets of protons. In A type of proton we have two protons, in B set we have three protons. And okay, here the distance between B type of protons and electronegative group is high, so therefore its chemical shift value is low, and the chemical shift value for A type of protons is high. Okay, the de-shielding effect is high for A type of protons compared to B type of protons. Okay, so as the distance between electronegative atom and proton increases, then what happens to chemical shift? Decreases, and chemical shift decreases. So the chemical shift of A type of protons is more compared to B type of protons. Okay, this is electronegativity. And so second one is anisotropic effect. Anisotropic effect, it is nothing but distribution of secondary magnetic field, distribution of secondary magnetic field or induced magnetic field non-uniformly throughout the molecule. You know, electron cloud, electron behaves like a teeny magnet. It also produces some magnetic field that is called secondary magnetic field or induced magnetic field. If that secondary magnetic field distributes non-uniformly throughout the molecule, it is not distributing uniformly throughout the molecule, okay, then such effect is called anisotropic effect. And for example, if you see chemical shift values for ethane, ethylene and ethine, chemical shift values for ethane and ethylene and ethine based on electronegativity of carbon. And so if you see electronegativity order for sp3 carbon is less than sp2 carbon is less than sp carbon. So as electronegativity of carbon increases, what about chemical shift of protons attached to carbon? Chemical shift values increases. As electronegativity increases, chemical shift values increases. So therefore chemical shift values, if you observe for ethane, okay, ethane, ethylene and ethine will be like this based on electronegativity. Based on electronegativity of carbon, this should be expected order, and this is the expected order of chemical shift values. This is the expected order of chemical shift values. Okay, as this carbon electronegativity is high, its chemical shift value may be high. But actual order, if you see, CH3 is less than CH triple bond CH is less than CH2 double bond CH2. But actual order is what? Okay, ethylene protons chemical shift values are more compared to acetylene protons. Ethylene protons chemical shift values are more compared to acetylene protons. Why? We have to see, and that we can explain based on anisotropic effect, and that we can explain based on anisotropic effect. If you see ethylene, when we are taking ethylene in the presence of magnetic field, it takes orientation like this, and it takes orientation like this. Let us consider this is the direction of applied magnetic field. So here whatever the electron cloud we have in between two carbon atoms, that produces magnetic field, that is called induced or secondary magnetic field. This secondary magnetic field distributes like this only. This secondary magnetic field distributes like this. Okay, so whenever the secondary magnetic field is distributing like this, okay, this induced magnetic field is in the same direction to applied magnetic field or opposing applied magnetic field. The induced magnetic field is in the same direction to applied magnetic field. The induced magnetic field is in the same direction to applied magnetic field. So therefore what happens to effective magnetic field felt by the protons, and effective magnetic field felt by the protons increases. That means fractional frequencies increases or Larmor frequency increases. So chemical shift values increases. And okay, here whether induced magnetic field is distributing uniformly or not distributing uniformly. Induced magnetic field is not distributing uniformly. See here, in this region it is opposing applied magnetic field, but in this region it is aligned with applied magnetic field in the same direction to applied magnetic field. So secondary magnetic field is distributing non-uniformly, so it is called anisotropic effect. So because of anisotropic effect, the protons present in shielding zone or de-shielding zone, and de-shielding zone, protons falls under de-shielding zone, or this is also called as paramagnetic zone. De-shielding zone or paramagnetic zone, that's why chemical shift value for ethylene proton increases. And okay, similar we can explain for benzene also. And in the case of benzene also, induced magnetic field distributes such that the protons fall in de-shielding zone or paramagnetic zone. That's why the chemical shift values for protons in benzene is high, around 7 we have the chemical shift values. Okay, next one, acetylene. If you take acetylene, takes orientation like this, and acetylene takes orientation like this in the presence of applied magnetic field. Okay, now the induced magnetic field distributes like this, and the induced magnetic field distributes like this. So you may observe. Okay, now in this case, whether photons fall under shielding zone or de-shielding zone. So where we have protons, the induced magnetic field is opposing applied magnetic field. Where we have protons, the induced magnetic field is opposing applied magnetic field. So therefore effective magnetic field felt by the protons decreases. So therefore fractional frequency decreases. So chemical shift values also decreases. And so carbon sp hybrid carbon. So we are expecting the chemical shift values may be high for these protons, but because of anisotropic effect, the chemical shift values are decreasing. Okay, here also the induced magnetic field is not distributing uniformly. Protons fall under shielding zone, and or it is also called as diamagnetic zone. Protons fall under shielding zone or diamagnetic zone, right? So next one, spin-spin coupling or spin-spin splitting, and spin-spin coupling. This is important. Spin-spin coupling for all competitive exams important. Spin-spin coupling. And okay, so if you take a sample having more than one equivalent protons, and This coupling is observed in the case of sample having more than one equivalent protons. Okay, whenever more than one equivalent protons we have, non-equivalent protons we have, the coupling between the protons may takes place, and the coupling between the protons may occur. Coupling between the protons may occur. Interaction between the protons may occur. Because of that interaction, the signal, NMR signal may split into many lines, and splitting of NMR signal is observed. That is called spin-spin coupling. And okay, whenever protons present in different chemical environment, they undergo coupling or they undergo interaction, then NMR signal split into many lines. Such phenomena is called spin-spin coupling or spin-spin splitting. And okay, why this splitting is observed? That splitting is observed due to one proton, one nuclei experience different magnetic field from neighboring nuclei. Okay, the one nuclei may experience different magnetic fields from neighboring nuclei. Because of that, okay, different magnetic fields means different Fresnel frequencies we will get. So because of that, one signal may split into many lines, and this is called spin-spin coupling or spin-spin splitting. And if you see the examples, you will get clarity. For example, I am taking like this, and here I am taking a sample with two different protons, and the chemical environment of A is different from B. So two sets of protons we have, A type of proton and B type of proton. So therefore, how many signals we will get in the NMR spectrum? We will get two signals in the NMR spectrum. One corresponds to A, another one corresponds to B. And okay, and now if you concentrate on a signal for A, and okay, we are getting two signals, and HA, one signal for HA proton, another signal for HB proton. This is the signal for reference proton, for example, okay, which is attached to high, more electronegative group. Its chemical shift value is high, and okay, right. HA proton, if you see, now for HA proton, how splitting of signal is observed because of HB proton. While HA proton interacts with HB proton, it experiences two different magnetic fields, and HA proton experience two different magnetic field. That's why the signal for HA proton split into two lines, and the signal for HA proton split into two lines. Similarly, HB proton experience two different magnetic field from HA proton. So HB proton signal also split into two lines. How HA experience two different magnetic field from HA proton? If you see, for HB proton, two possible orientations we have: upward orientation or downward orientation with 50-50% probability, or 1:1. Okay, with 50-50% probability we have. Okay, HB proton may take either upward orientation or downward orientation. If HA proton interacts with upward orientation, its effective magnetic field increases, so its Fresnel frequency increases. And when HA proton interacts with downward orientation of B, when HA proton interacts with downward orientation of B, it experiences effective magnetic field felt by the HA decreases, so its Fresnel frequency decreases. And okay, so initially we are getting HA proton like this, and HB proton like this. That is some reference proton. Now this is in the without coupling, and let us consider without coupling. And now because of coupling of HA proton with HB proton, it's split into two lines, and like this. And this is actual its delta value. And so see here, delta value is increasing and delta value is decreasing. Okay, when it interacts with the upward orientation, delta increases. When it interacts with the downward orientation, delta value decreases. And similarly for HB proton also. HB proton may interact with HA proton, but for HA proton, two possibilities we have: upward orientation and downward orientation with the same probability, 50-50% probability, 1:1 probability. So therefore, this is actual delta value, chemical shift value for HB proton. Hb proton. So when it interacts with upward orientation, its chemical shift increases. Upward orientation of A. When it interacts with downward orientation of A, its chemical shift value may be decreases. And so this is a delta A, this is a delta B, and so this gap is said to be what? Delta AB, and that gap is called as delta AB. That is the difference in the chemical shift values of A and B, and that is the difference in the chemical shift values of A and B. And here we will get two lines, and one line split into two lines with 1:1 intensity ratio. And intensity ratio of these two doublets is 1:1, and since 50-50% probability we have for upward orientation and downward orientation, that's why the intensity of multiplet, if you see, doublet, if you see, 1:1. I'm giving some more examples for spin-spin coupling. For example, we are taking like this end. The bonding connectivity of these two protons are different. These two protons bonding connectivity is same. So here AB2 type of molecule we are getting, AB2 type of molecule. In one type, in A set one proton is there, in B set two protons are there. Overall, how many different types of protons we have? Two different types of protons we have. So we'll get two signals, and two signals. One corresponds to one HA and another one corresponds to 2 HB, and one corresponds to 1 HA and another signal corresponds to 2 HB protons. And now what about splitting? If you consider HA proton, okay, here how many HB protons are there? 2 HB protons. HA proton experience how many magnetic fields? How many types of magnetic fields from 2 HB protons? If you see, 2 HB protons may take place both upward orientation, or one upward, one downward, or one downward, one upward, or both may take downward orientation. Both may take downward orientation. So A type of proton may couple with 2 HB protons of this orientation or this orientation or this orientation. The possibilities are 1:2:1. Both with upward orientation, one possibility we have. One upward or one downward, or down or upward, two possibilities we have. Both with the downward orientation, one possibility we have. So in the absence of spin-spin coupling, this is the signal for HA. Let us consider. Okay. Now HA experiences how many magnetic fields from HB? 3 different magnetic fields from HB. 2 HBs. HA experiences 3 different magnetic fields from HB. So the signal for HA is split into 3 lines, and the signal for HA is split into 3 lines. The intensity of the signals is 1:2:1. 1:2:1. And so in the absence of magnetic field, we have HA proton signal like this, and HA proton signal like this. In the presence of in the presence of spin-spin coupling, and in the absence of spin-spin coupling, we are getting like this. In the presence of spin-spin coupling, we may get like this. So this is the actual delta value, and that is the actual delta value. Center we have to take, and to give chemical shift we have to take center, and we have to take center. So 1:2:1 intensity, and 1:2:1 intensity. This is called as a triplet, and so one line split into 3 lines, that is called as a triplet. What about the intensity of lines in the triplet? 1:2:1. And now if you see for HB, and what about the signal for HB? How many neighboring protons are there? Only one neighboring proton, that is one HA. For HA, 2 possibilities we have. One upward orientation, one downward orientation with 1:1 probability, 50:50 probability. So therefore, the signal for HB split into how many lines, and the signal for HB split into 2 lines only. The signal for HB split into 2 lines with 1:1 intensity ratio only. Okay, so we may get like this, and for HA proton and for HB proton. Okay, the HB proton signal intensity is more compared to HA proton, since it is due to 2 protons only. Hb proton signal is due to how many protons? 2 protons. Ha proton signal is due to only 1 proton only. So the signal for Hb proton is more, okay, intensity compared to Ha proton only. So for Ha we will get triplet, for Hb we will get a doublet only. Doublet whose intensity is 1:1. Here whose intensity is 1:2:1. 1:1. Okay. Similarly, if you take like this and Ha proton, Hb protons. For example, we are taking like this and Ab3 type of molecule we are taking. Okay, how many types of protons we have? 2 types of protons we have. So we'll get 2 signals. One corresponds to 1 Ha proton, and the second one corresponds to 3 Hb protons. One corresponds to 1 Ha proton, another one corresponds to 3 Hb protons. Okay. So now if you see the signal for Ha split into how many lines? Okay. So what are the possibilities for these 3 protons? And the 3 protons may arrange like this, all with upward orientation, or 2 upward, 1 downward, and 2 upward, 1 downward. For this, how many possibilities we have? 3 possibilities only. Downward, upward, upward. Next, downward, upward, upward. Next one, both with downward, one with upward. And for this again, 3 possibilities we have. Okay, all with downward orientation. All with downward orientation. So the possibilities, if you see, 1:3:3:1. And the possibilities, the probability for these arrangements, the probability for these arrangements is 1:3:3:1. So Ha may experience how many types of magnetic fields from 3 Hb protons only? Ha may experience 4 types of magnetic fields from 3 Hb protons. So therefore, the signal for Ha split into 4 lines only. The signal for Ha split into 4 lines. What about the intensity ratio? 1:3:3:1. So center we have to take, this is chemical shift of Ha proton only. That is the chemical shift of Ha proton. This is called as quartet only. That is called as quartet. And similarly for Hb proton, only one neighboring Ha proton is there. So it's split into doublet. And for Hb proton, what we will get? Doublet. Only one neighboring proton is there. Okay, 2 orientations. One is upward orientation for Ha and a downward orientation for Ha. So therefore we will get doublet for Hb. Okay. So in general, if n neighboring nuclei are there, if n neighboring nuclei are there, if a nuclei interacts with n neighboring nuclei, then the signal split into 2Ni plus 1 lines. And the signal split into how many lines? 2Ni plus 1 lines. If a nuclei interacts with n neighboring nuclei, then the signal split into 2Ni plus 1 lines. And if you take proton NMR spectroscopy, H1 NMR spectroscopy, okay, what is the number of lines we will get in a multiplet? And if n neighboring protons are there, what is the number of lines we will get? And so that is 2Ni plus 1. We have 2 into n into, what is I for proton? And 1/2. So 2 gets cancelled. So therefore we will get n plus 1 lines. And that means if 2 neighboring protons are there, 3 lines. If 3 neighboring protons are there, 4 lines. If 4 neighboring protons are there, 5 lines we will get. And okay, for example, we are recording proton NMR spectroscopy, and we are recording proton NMR spectroscopy. Okay, we are taking HD, and for example, proton interacts with what? Deuterium. What is I value for deuterium? I value for deuterium is 1. So therefore, how many deuterium atoms are there here? Only one deuterium atom is there. Only one deuterium atom is there. So proton may interact with this one deuterium and 2Ni plus 1. So the signal for this proton split into how many lines? The signal for this proton split into how many lines? 2Ni plus 1 we have. Number of deuterium atoms 1. I value for deuterium 1. 2Ni plus 1. So that means the signal for proton split into how many lines? 3 lines. And the signal for proton split into 3 lines whenever it interacts with deuterium. Okay, since I value for deuterium is 1. Okay. So if you consider only coupling of protons with protons, and if you consider the coupling of protons with protons, the number of lines obtained is n plus 1, and since for proton I value is 1 by 2, 2 gets cancelled, so we will get n plus 1 lines. So we can give what about intensity of multiplet, and what is the intensity of multiplet that we can give based on Pascal triangle, and okay, for example, if the number of neighboring protons, I'm indicating n, we have like this 1, 2, 3, 4, 5, 6, then how many lines we will get in the multiplet, and multiplicity, and number of lines in the multiplet is what? N plus 1. If you take proton NMR spectroscopy, and proton NMR spectroscopy, the number of neighboring protons are n, the number of lines obtained is n plus 1, that is 2, 3, 4, 5, 6, 7. Okay, the designation of that multiplet is, this is called doublet, and doublet we may indicate with the D. This is called what? Triplet, we may indicate with the T. This is called what? Quartet, Q, pentet, quartet, pentet, next sextet, heptet, and heptet, or septet, septet or heptet. This is the designation, and 2 lines means doublet, 4 lines quartet, 7 lines septet or heptet, 6 lines sextet. And next, what about intensity ratio of the lines, and intensity ratio of the lines, okay, that we can give based on Pascal's triangle, and that is called Pascal's triangle. Okay, intensity ratio here 1:1, next 1:2:1, 1:3:3:1. Okay, Pascal's triangle will be like this, and 1, 1, 1. Next we have to add and 1. Okay, first every time left side we have to take 1, and okay, 1 plus 1, 2, next 1, triplet in the case of triplet. Next we have to start with 1, 1 plus 2, that is 3, 2 plus 1, that is 3, next 1, quartet, and 4 lines. Next we have to start with 1, 1 plus 3, that is 4, 3 plus 3, that is 6, 3 plus 1, that is 4, again last we get 1. This is called Pascal's triangle, and so like this we will get intensity ratio. And so for pentet, what about the intensity ratio? 1:4:6:4:1, and otherwise we can write directly like this, and every time we have to start with 1, end with 1, and 1 all with upward orientation, all with downward orientation, and only one possibility we have, all with upward orientation, all with downward orientation. 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, next 1. Next 1:1 plus 5, 6, 5 plus 10, 15, 10 plus 10, 20, 10 plus 5, 15, 5 plus 1, 6, and last one 1. And so this is the intensity ratio of the signals present in the multiplet that we can give based on Pascal's triangle. And okay. And last one, this is also important, coupling constant. And so in the next class we will see some questions, and based on all these spectras. Coupling constant. Okay, coupling constant is nothing but the distance between any 2 lines, adjacent lines in the multiplet, and the distance between any 2 adjacent lines in the multiplet, that is called coupling constant. And okay, we have a multiplet like this, any 2 adjacent lines we can consider, and any 2 adjacent lines, otherwise we may take like this, and this is actual delta, and this is actual delta chemical shift value. Okay, we are getting like this, and this peak we are getting here, this peak we are getting, the gap is called what? J, and J is called as coupling constant. Coupling constant indicates the extent of interaction between 2 protons and extent of interaction between neighboring nuclei. The extent of interaction is high, the coupling constant value is also high. So order of interaction between two nuclei that we can give based on coupling constant. If extent of interaction increases, coupling constant also increases. And generally coupling constant is expressed in Hedges. And we saw chemical shift, if you express in Hedges, what is the drawback? It is field dependent and instrument frequency dependent. That's why instead of Hedges we followed ppm scale. And but chemical shift, coupling constant, if you see in Hedges, it is independent of field, and instrument frequency. That's why we can express coupling constant in Hedges also. Since coupling constant in Hedges is independent of field and instrument frequency. And okay, for example, if you take this molecule, and how many types of protons we have? Two types of protons we have, Ha, Hb. Ha couples with Hb, Hb couples with Ha, so therefore we will get doublet for Ha and doublet for Hb. We will get doublet for Ha and doublet for Hb. So A interacts with B, B interacts with A. So extent of interaction between A and B is same. So therefore coupling constant value is same in both the cases. And coupling constant value is same for both the cases, Ha, Hb. And this is the chemical shift values of A and B. And center point we have to take chemical shift of A and B. The gap is called delta AB. Okay. Now J value in Hedges depends on instrument frequency or not depends on instrument frequency? Not depends on instrument frequency. That I will explain by an example. In Hedges, and J value in Hedges. For example, on 100 megahertz instrument we are taking it. On 100 megahertz instrument, coupling constant is 0.1 ppm. Okay, this gap is 0.1 ppm. And 0.1 ppm means in Hedges how much we will get? And 0.1 into on 100 megahertz instruments, each ppm is equal to 100 Hedges. Each ppm is equal to 100 Hedges. That means 0.1 ppm means how much we will get? 10 Hedges. And 10 Hedges we will get. On 100 megahertz instruments, J value is 0.1 ppm. Then coupling constant in Hedges will get 10 Hedges. And if you take on 200 megahertz instrument, on 200 megahertz instrument, J value we will get, we may get 0.05 ppm. And in ppm it changes, and J value we may get 0.05 and in ppm. So therefore in Hedges if you calculate 0.05 into 0.05 into 1 ppm is equal to how many Hedges? And 200 Hedges. 200 into 0.05 means again what we will get? 10 Hedges only we will get. In ppm it changes, and but chemical shift, coupling constant in Hedges remains constant. And that's why generally coupling constant is expressed in Hedges. And coupling constant is expressed in Hedges. Okay, this is the concept of coupling constant. And so I will give some questions also. And if you see those questions you will get clarity. Okay, in the next class overall I will give some questions from microwave spectra, IR spectra, Raman spectra and NMR spectra. Right? Thank you.